turn the recording off maybe when Don's done, or at noon, or at some reasonable thing, as I've got to bail. So those of you that are here, thank you so much, and I'll see you next month. But on with the show.
Okay, let's see here. Share screen. Hang on one second. Let's see, where's chat? Okay, I think this is the link. So I'm going to be talking, that should be the link to my old talk about the project that we're doing. All right. So what I'm going to do is I'm going to just go over source code here. We've been working on our FPGA, I call it the Core 1 project, CISC over RISC engine. And we're building a 32-bit fourth processor in very high level behavioral system Verilog. So you notice there isn't a whole bunch of modules in here. Okay, so let's go with this guy. So we have a parameter. This is the data width of the system, which is a 32-bit system. The characters are 8 bits wide, so you subtract 1 in Verilog. But usually it's like 32 minus 1, or just make it a parameter 31. Address size we just kind of set for 9 because we don't have too much address in the dictionary as of yet. So we're going to be talking about the outer interpreter. Dimitri did this coding and he has COVID. And so I kind of got a quick lesson on it earlier today. At some point I was going to, if he was available, I was going to let him talk to this, but I pretty much got it down. So what we have is we have a dictionary and we have an execution token list. So think of it this way: you have a word list, right, which is one part of the dictionary, and based on the word's position in that list, like word number 1 points to execution queue position number 1. Word number 2 points to execution queue number 2 slot. So that's the way this code is implemented. So what happens is it will parse the ASCII characters from the RS-232, and then it will look it up and find out the execution token, and then execute it out of our boot ROM. So let's just take a look at the boot ROM for just a minute here. So this is a typical, this is a boot ROM in our system, and you can write, these are basically opcodes in that our core processor can execute. And so you notice there's a number over here, position 1. If I jump to position 1, I'm going to start executing here. If I jump to position 21, I'll start executing right here where it processes number. And there's a little bit later on, that'll be important. So we have a register, an 8-bit register called byte in. Now these always, whenever you see an always, it means that it's a parallel task inside of an FPGA. We have a word pointer. This is the dictionary size. This is the word in register. You note that it's 32 bits wide. So the word in register actually holds the count, and then 3 characters is the very first part of the string, We need to expand this so it goes past that, but right now it is working with just using the count and 3 characters. So we have a local execution pointer right there. We have enum that defines the state machine. Here we're creating a simple little dictionary. This would be in RAM. Right now we're just doing it in logic just for testing the algorithm. So basically it's a table that's 32 bits deep and 4 characters wide. We are initializing it with red, GRE for green, BLU for blue, and DEL for delete. Okay, on reset, we just initialize everything. So the idle state, we set the word pointer to 0. We tell the UART, no, not to receive, I guess. The UART RX data, so this is an 8-bit register that the UART is capturing the 8-bit data in. So we're just equaling it to byte in, and we're changing the state to parse. So then we go down to parse. So XT pointer, we're gonna increment the XT. This is the execution token pointer, and we're gonna assign that XT position, which is starting at 0, to the local XT register. We're setting the register to 0 here. Then the next state is execute. Else, so we're going to implement that. We do that stuff. This one is the, so this is the word in. Remember, this is a 32-bit register. So we're looking at just the top character, the top 8 bits. And if it's less, if the top 8 bits are less than 3, then we're going to basically store the byte in on these, just stuffing this this 4-character register with these 3 bytes here. And we're going to increment the word pointer there. I'm sorry, we're going to increment the that's actually the count, and then it goes to search. And then and now the search, we are using a 12 megahertz clock. The search can find a word in well, basically can do a compare 12 million times a second. You know, if you have 3 things you know, in the list, obviously, then it may look at all 3 of those, so it'd be 1/3 of that. But the search routine, if it finds it in the first slot, is 12 million times a second. So if the dictionary name is equal to word in, then we basically are going to update our local execution pointer register with the dictionary word pointer. So if it's an offset of 2, say, then it would set this to 2, and then it would come down here and then it execute the execution pointer in the queue there, or it's going to convert it to a number. This is pretty interesting right here. When I talk about using a high-level system Verilog, everyone says, "Oh, you know, it's Verilog, you know, so what?" Well, see, this inside function is in system Verilog, and what it says is, if it's inside from ASCII 0, because there's a string quote around 0 and a quote around 9. If it's inside those 2, which means it's an ASCII number, right? Then it's going to be true. And if it's true, then we'll set 0 to byte in. and we'll execute 21. Now remember, 21 is right here, so it's going to execute number. So this is kind of a way, so you can have, because we're using a pointer into the boot ROM, that pointer could be in RAM, it could be external memory, it could be anywhere. So right now we're just using the boot ROM to debug all this. And then you come down here and you execute. So basically, as long as the execution read pointer and the write pointer aren't, as long as the write pointer is less than the read pointer, then we're gonna execute this and tell the UART to go grab another character. So boot ROM. So what's going to happen here is, I actually have a video here, so hang on a second. This is an example of Dimitri. Actually, so he's got a, this is a terminal on a PC, and it's just a transmit and receive line, you know, RX and TX, and you'll see that he's gonna enter red or green, which is green is GRE, and you can actually see the LEDs light up down here. Can you guys hear Dimitri? He's typing in red.
I cannot hear him speak, but I can see the video.
Yeah, okay, he just typed in blue, BLU. He just typed in green. And so that shows that we're actually, this code is executing. So I basically want to give you guys an update as to what we're doing. This outer interpreter is not completed yet. We have to add, we have to be able to, you know, have strings longer than just 3 characters, obviously. So we have to add, you know, when it tests. But the interesting thing is it can test 32 bits at a time. So it's very fast. So we finished the outer interpreter. The last thing we have is the compiler. So one of the things I asked you know, the group to do today is to open it up for conversation as to things like state versus stateless, you know, compilation, different ideas you guys have on developing the compiler. That's the very last thing we're going to be working on. Anybody have any questions on the source code before I stop sharing? No questions?
I have a question.
Okay.
If I understand this correctly, you are making an FPGA as an interpreter machine.
We're building a full 4th computer inside of an FPGA. It's got, so you basically hook up a serial, you know, 2 serial lines to it, and you have a complete system. You can also clone the system, so you can have multiple cores inside. We will have networking of cores inside the FPGA. Right now, this is, we're using a development board that costs $24. It's using the Lattice FPGA, and the Lattice FPGA costs $4.50. It's got over 4,000 LUTs, and we're only using 27 LUTs right now. LUTs is the amount of fabric inside the FPGA. So we're using about 55% of it.
If we wanted to duplicate what you were doing, is there a posting somewhere that shows, like, you know, buy this, buy that little board, buy this, and download this software?
I'll tell you what, yeah, I need to, I've actually kind of started on that, but I haven't released it yet. Let me work on that. And if you're on the SVFIG mailing list, I'll send it out. Or you can, I'll put my email address. Go ahead and send me an email, and I'll let you know when it's ready. So
Great,
we're not, Yeah, we're not quite ready. What I really wanted to do before I send it out to people was to actually have a fully working system. So we're probably a month or two away from that, but we're getting very close. Like I said, we're basically the outer interpreters work. The inner interpreter is working great, and we have implemented fourth opcodes in System Verilog. A fourth opcode many times, or what is one line of code. You know, it might be up to 3 lines. The idea behind this whole project is to experiment with computer architectures. The fourth engine will be the basis of that. Dimitri has written a prologue in fourth with 400 lines of fourth code. We're probably going to implement, just take the functionality. There's about 7 words that you would implement to give you the prologue capability. We'll probably just make them fourth words and not try to be syntax compatible with prologue. But you can, so the basically the microprocessor engine is very small, and it's working great. And now we're building the entire fourth computer in System Verilog. We just hook up a terminal. And if you want to play with FPGAs, it's really cool because you create your code and you make an always statement that is operating in parallel. This is a massively parallel computer, especially when you write your device drivers and things in System Verilog, and then you just read and write to registers from fourth. So you can kind of bit bang these registers and control this new System Verilog code that you wrote, and use fourth as the debugger on the FPGA. So I think that it would be a good way for people to get their hands on FPGAs and play around with them.
I would love to have a copy before you have it completely ready.
Okay, sure. You got it. I did set up a users a group on Facebook. I called AI and Robotics because it's not just going to be this fourth. We're going to be talking about AI and robotics. I'm going to put this in the chat here. So if you go to that group, it's a private group. I'll let you in. Yes, it's going to be open source. So click on that link there. I just made it open to the public, searchable by the public. So maybe you guys can be my guinea pigs. Click on there and see if I get notified to let you in. Otherwise, send me an email, and we will share the source code with you. We have a GitHub set up for this, and it's on one of the branches in the GitHub right now. So can we open it up to some of these gurus out there, like Brad?
Thank you very much.
You're welcome. So what do you guys think of the state versus stateless? I know, like Peter Jackie, I tried to get, he was going to give a talk because he's done some pretty interesting things with his propeller fourth. He calls it tachyon fourth for the propeller board. So what do you guys think of state versus stateless? What kind of thoughts do you have on, now that we're finishing up the outer interpreter compiler, any ideas that you guys might give us? Well,
to me, you should enable both, because sometimes you need one and sometimes you need the other. I mean, it's better to do stateless, but sometimes stateless is really hard. And sometimes you absolutely need state. So to me, you got to do both, or
okay.
at least enable both to be done. I mean, I prefer I sort of prefer to do cooperative multitasking because it's so much more repeatable and like predictable. And then you go to the preemptive when you have to. So maybe a couple preemptive channels and then a bunch of different things on each cooperative channel within the preemptive is how I get the maximum performance anyway.
Yeah, on an FPGA, you want to go with multiprocessing rather than multitasking.
Of course, I wasn't thinking that. Sure, right.
But in the fourth processor itself, yeah. So what you want to try to do is, where possible, write it in system Verilog. Think of it like a device driver, but it's running a parallel process at up to 250 megahertz. So your fourth processor can be running at somewhere between 100 and 200 megahertz. But all these little tiny system Verilog modules are running independently and just sharing a register that the fourth can read and write to. The other thing is, I gave a talk on my triune operating system, which kind of has a unique multitasking feature. And I won't go into it right now. Maybe I should give another talk on that. But I'm going to implement that. But we will have a version of this, a branch of this always. So you just have your basic fourth that you want to play with the system. You can start with the basic one, and then we'll have a branch that uses the complete triune OS, and the triune language for intelligent robotics will be coming on top of this also down the road. And I'll finally, have a fourth board for this. Oh, and I was thinking in terms of development boards. So I've already bought the parts. I have a 43,000 lattice part that cost like, I think it was $7 or $8. And then I'm going to I got ADCs. So I'll put some ADCs on the development board, some DACs, even a power amplifier for Dr. Ting, so he can do stereo audio. Dr. Ting likes to play music on stuff. And, but I'll have 3 DACs, and I'll bring it out to a VGA connector. And then it also will split off to a power amplifier and then to a speaker connector. But with the VGA connector, if you want to play around with VGA, you can do that. I also want to, you can see that it's a display. It's kind of hard to see, I guess.
Yeah,
but anyway,
you're green screening it.
I know. Yeah, so it's it's basically a display, 7-inch display. I'd like to hook that up, and it might be interesting to have either have a system Verilog display driver, or you could instantiate. So in the 43,000 LUT chip, you could instantiate 10 or more of these 32-bit fourth processors with associated high-speed SRAM internally, or have external SRAM. So what I was thinking of is you have one master processor that hooks to your serial port, and then you can put external RAM on that one. And then the ones inside, if you want to have them running some other task, like maybe you want to have one running the display, for example, and then you'd have an internal FPGA networking of these guys. And you can experiment with multi-core if you want.
For a synthesizer, an audio synthesizer, that'd be great, because you could have so many different voices. You could do a whole orchestra.
Yeah, and I'm putting ADCs on there, and I'll have a microphone input because I want it for a robot, and I want the robot to be able to listen and talk, right? Both. So I might even put stereo microphones on there. then you could do, I probably will, because then you can do kind of a direction stuff, you know, try to triangulate where a sound is coming from.
Can I have the floor?
What was that?
So I would like to strongly discourage you from going the multiprocessing route if this is not absolutely necessary because of performance problems. Because with multiprocessor, you run in a whole nest of problems relating to mutual exclusion and how to handle the peripherals. And
no, you don't.
If you have a multitask force system, then everything becomes very simple because it is not actually multitasking, it is pseudo-parallel, which means at any given time, only one process is active that wants to access a resource. And so it is sufficient for the resource to send out a busy signal, and the busy signal can be read. And if the resource is busy, then the task that needs it can go to sleep and wait until the busy signal is no longer active. Whereas if you have a multiprocessor system, every process that needs a resource has to run 2 lines to the resource, which are request and grant back, and then you have to use a priority encoder, and that is just, I mean, eats up resources.
Okay, let me explain how you do this, because we've actually done this at work, so I know that it works. So what you do is with multiprocessing, you write. Are you familiar with FPGAs? You know what an always statement is? Always statement. Okay, so an always statement is a process, right? It's an infinite process, a loop. You conceptually, what you do is you create registers for each process, and Forth can go grab the data or store the data in those registers to communicate with this process that's running asynchronously. So you don't need to do any you don't necessarily need to do any handshaking unless you want to. You could make a register, for example, you can make a register with flags in it. Let's just say that there's some external process. Let's say you're digitizing and you want to interrupt the fourth processor when an event happens. You can create a register that can interrupt the fourth processor, or it could be read by polling, either way. Now, remember, I said I'm going to implement multitasking inside the fourth core, so it will work. I've done it before. We're doing it at work right now.
Yeah, I don't quite understand your approach, but good luck.
All right, well, thank you. I really appreciate the input.
I'm going to go ahead and stop the recording since we're just having a chat, and it'll save me editing trouble later. So